We've been told that history is written by the winners, but I think it's more accurate to say that history is often hidden by the atmosphere. For 200 years, we've looked at the early 1830s as a period of climatic weirdness, a ghost story whispered in old weather logs about crops dying in midsummer, and frost creeping into July like a thief in the night. But here's the mystery we've been ignoring. How does an entire planet's thermostat get hijacked overnight without anyone seeing the person holding the dial? We know that it happened. The year without a summer was real, visceral, and terrifying. But until very recently, we couldn't find the culprit. It was like looking at a crime scene where the weapon had evaporated into thin air. Today I want to take you on a journey to crack that case wide open. We're going to look at the terrifying Blue Sun accounts from 19th century survivors. We'll explore the high-tech forensic detective work happening inside ancient ice cores. And finally, we're going to uncover why the location of this specific eruption changes everything we thought we knew about Earth's geological vulnerability. To understand how big this is, you have to imagine being alive in 1830. This was the dawn of the industrial age of time, when humanity felt it was finally beginning to master the world. And then, the sky broke. It wasn't a gradual change, it was an atmospheric coup d'etat. People began reporting that the sun didn't look like a golden coin anymore. It looked bruised. Blue, a sickly translucent orb hanging in the sky choked with dust and sulfur. This wasn't just bad weather. For the people of the 1830s, farmers who lived or died by the season it was supernatural. They watched their wheat wither while it should have been ripening. They saw snow fall on green fields in June. They were living through a global famine triggered by a geological sneeze we couldn't see coming. And for nearly 2 centuries, scientists have been playing detective, trying to figure out which mountain threw the punch. Some blame volcanoes in South America. Others look toward the Pacific Ring of Fire. They had theories, but they lacked the fingerprints. That's where the ice comes in. Think of glaciers not just as frozen water, but as Earth's hard drive, a literal archive of every breath the planet has taken for hundreds of thousands of years. By drilling deep into the hearts of Greenland and Antarctica, we can extract time capsules. When a volcano erupts, it shoots sulfur dioxide into the stratosphere. These particles travel around the globe like a veil, eventually falling as ash or sulfate deposits onto these polar sheets. By analyzing the chemical signature in those layers, we can reconstruct the atmosphere of 1830 with terrifying precision. And this is where our detective story takes its first major turn. For years, many believed that because the cooling was so widespread, it had to be one of the massive supervolcanoes we already knew about, the giants like Yellowstone or those in the high Andes. But the data just came back from the ice cores, and it's telling a different story. The smoking gun is a glaring geographical imbalance. The analysis shows that there is roughly 6.5 times more sulfur fallout in Greenland than in Antarctica around 1831. That's not just a small difference, that's an atmospheric scream from the north. While this doesn't give us one single name on a map, it effectively narrows our search by ruling out many of our favorite southern hemisphere suspects and pointing toward a northern epicenter. If you want to find the culprit, you have to look at where that sulfur was heaviest. This discovery shifts the entire search toward a specific northern region we previously overlooked because it didn't fit our super eruption narrative. It suggests that this wasn't necessarily one gargantuan explosion of an iconic volcano. It could be a more localized, yet incredibly potent, release from a northern high activity zone. This is where things get weird and, honestly, kinda humbling. We often assume that for something to change the entire planet's climate, it has to be some world-ending, Mount Doom-style apocalypse. But this data suggests a different reality. The smaller giants matter just as much. An eruption doesn't have to be the biggest in human history to be catastrophic. It just has to be positioned correctly. Release enough sulfur into a specific layer of the atmosphere, and let the jet streams do the heavy lifting. It's about atmospheric geometry as much as raw power. Think about that for a second. We are looking at a system so interconnected that a single mountain, thousands of miles away from your backyard, can decide whether your crops grow or rot. It's the ultimate reminder of our fragility. In 1830, people thought they were masters of their fate. In reality, they were passengers on a planet with some very volatile roommates. Now, I want to pause for a second because this is where the why does this matter part hits home. We spend so much time talking about long-term climate trends, the slow burn of carbon emissions and rising temperatures. But this 1831 data reminds us that Earth also has its own internal thermostat that can be hijacked in an instant by a geological sneeze. If you're finding this journey through history and chemistry interesting, drop a comment below what part of our planet's hidden history fascinates you most. Is it the geological giants we see today, or the ones still sleeping under the ice? Let's look at the counter-arguments for a moment. Some might say, well, if we don't know exactly which mountain it was yet, does the data really matter? But that's like saying because you haven't found the specific thief, the robbery didn't happen. The fact that it was northern tells us where to point our sensors and what kind of geological signatures to watch for in the future. It forces a shift in how we think about monitoring. We shouldn't just be looking at the famous, well-studied volcanoes with their tourist centers and research teams. We need to be looking at the quiet zones. The northern volcanic arcs that are less explored but have the potential for high sulfate output. It's a move from reactive science to proactive surveillance. Compare this 1831 event to something like the Huayna eruption in Peru, one of South America's largest. While it was massive enough to cause global cooling, its location and chemistry meant it didn't leave that specific northern freeze signature as intensely as a northern hemisphere event would have. Every volcano has a unique atmospheric personality. The 1831 event is our case study for how an eruption in the north can effectively put the world into an atmospheric refrigerator. The irony, of course, is that we are currently living in one of the most complex climatic eras in human history. We're adding our own veils to the atmosphere with carbon and methane while these geological giants sit there, occasionally exhaling sulfur. It's like trying to manage a house where you're constantly turning up the heater, but every few decades someone else might come along and blast the AC on full power. The blue sun mystery isn't just an old news story about some weird weather in the 1800s. It's a piece of forensic evidence that reveals how thin the veneer of our stability really is. We used to think we were isolated from these events, but the ice cores prove otherwise. The planet doesn't care where you live. Its atmosphere is one big interconnected room. So what's the takeaway? It isn't that we should be terrified every time a mountain smokes, but it is wild to think about how much history was shaped by things we literally couldn't see, events so massive they were erased from our immediate memory but preserved perfectly in the ice of Greenland and Antarctica. We're learning that Earth isn't just drifting toward one inevitable state. It has these violent, sudden pivots. The 1831 data is our map for those pivots. It tells us that the ghosts of our past are actually fingerprints left in the frost reminders that we live on a restless planet with secrets buried deep beneath its surface.